a commonly used type of equipment throughout the world in industry, in aviation, in power plants, is a category of equipment called turbines. And so I want to provide you with 3 example problems, worked out example problems that illustrates how do you solve problems associated with turbines. So let's get started. I'm going to show you how to, not necessarily show you how, but maybe remind you how to determine the output power from a steam turbine, shown here, and also an air turbine, because these are both so commonly found in your homework problems, and ultimately these types of problems will be found in your practice of engineering. So we'll do a steam turbine example first, and then I want to do an example of an air turbine, both using the ideal gas model variable specific heat, and finish it up with the exact same problem using constant specific heat model. So first example, a steam turbine. And of course, what should come to your mind first is H2O. We've got a phase change substance. So we're going to be using the steam tables to evaluate the properties that we need to analyze our steam turbine. Now, I want to suggest that if I were teaching this course, if you were in my class, you would be getting a problem nearly exactly like this, either on a quiz or a test. So this is potentially a classic test prep problem for you. A fully insulated steam turbine operates with a throttle condition, that's inlet, of 4 megapascals and 400 degrees C, and a known steam flow rate of 12,000 kilograms per hour. Turbine outlet pressure is 40 kPa. Changes in kinetic energy are negligible. And of course, we know changes in potential energy are negligible. This is a turbine sitting on the ground, okay? Isentropic turbine efficiency is 80%. And the problem is one question: determine the power output from this steam turbine, the output power from this steam turbine. All right, this is what an industrial type steam turbine will look like that could be related to this given information. We've got steam, high pressure steam coming into the inlet of the turbine through this. This would be a governor that adjusts the rate of flow of steam into the turbine, into the first section. And notice these turbine blades. So these are various stages of a steam turbine. So the steam is expanding, it's dropping its pressure, it's expanding across these rotating blades. So you see the shaft rotating, it's causing the shaft to rotate at a certain speed and torque. That's what gives you this rotating output power. We call that W dot out. Finally, the steam expands to where it's really gotten a higher volume, high specific volume, lower density. That's why you see it expanding. And then here's sort of the exhaust region, and the steam is lower pressure steam is exhausted down through the bottom of this steam turbine casing. And it might go either to another process or to a condenser. Now, here's our equipment sketch, and notice how it's my hope that you see that the sketch is supposed to depict what a real turbine looks like. So that's why this turbine is depicted as a trapezoid with increasing area. We're trying to depict what a real turbine. Let's see. We've got M dot coming into the inlet state, exact same M dot leaving, because we've got a steady state, steady flow, open system with one inlet and one outlet. In the problem statement, it said there was no heat transfer, fully insulated. That's why I'm not showing Q dot on this sketch, but I am showing W dot out of the turbine. Turbine efficiency, 80%. This is plenty to go out and solve for W dot of the turbine. I hope you're thinking, before I show you how to do it, I hope you're thinking in your mind, how would I do this? How will I do this? Well, Of course, the first step is then to follow up your equipment sketch with a TS diagram, because we've got a phase change substance. And so it's my hope that you would recognize 4 MPa and 400 degrees C. That's hot, okay, as a superheated vapor. So you should plot down state 1 is in the superheated zone. You should recognize this for steam, okay? And the first thing we're going to do is study the isentropic process, the reversible and adiabatic process, and then we will apply turbine efficiency for the actual process. So this sketch starts showing the isentropic process, 1 to 2I, okay, down to a lower pressure, 4 megapascals. Here's our line of constant pressure, dropping down to a lower pressure, P2, 40 kPa, okay? So this is a nice professional quality TS diagram. Now, we're going to add an irreversible line. So this adiabatic process is a solid line. The dashed line represents an irreversible adiabatic turbine. So in other words, we cannot integrate under this path, okay, because it's a dashed line. You can't integrate under a dashed line. No, the path is not shown. It's an irreversible process. Now, the key is to also show the various properties and states on our TS diagram. Notice here 2I, that's the isentropic outlet. 2A, that's the actual outlet condition of the turbine. 2A for actual. Now, the textbook calls 2I, they call it 2S. Textbook also calls what I'm calling 2A, they call it 2. But you're going to be able to figure out the difference. I learned at 2A. It's easier for me to recall 2A is like 2 actual instead of just 2. That's why I call it 2A. All right. Here's the solution steps. Before we go and start crunching numbers, the last step is going to be, we're looking for power, aren't we? W dot. Okay. Well, what we're going to do is we're going to recognize that the power is m dot times little w. So in our detailed thermodynamic work, we're going to be looking at little w, kilojoules per kilogram. And then in the last step, we're going to multiply that by m dot to get kilojoules per second or kilowatts. All right. So the first thing I'm going to want to do is transform my given mass flow rate, which was kilograms per hour, into kilograms per second. I'm going to do that first. Then I'm going to study the isentropic turbine, recognizing that S2I equals S1. That's the definition of an isentropic reversible adiabatic process. We're going to use that to determine the quality under the dome. We're going to determine X2I in that manner, since we know the pressure, and then we know S2I. Once we know the quality, we will use that definition to determine H2I, the enthalpy of the isentropic outlet. Okay, so then we're going to determine the isentropic work, reversible adiabatic work, and we call that W sub I, little work sub isentropic, using the first law, steady state, steady flow, open system, one inlet, one outlet, first law. Finally, then we'll apply the turbine efficiency to determine W actual, and then get down to W dot. That's what we're looking for, is the output power. And so I'm going to go a lot faster on the next two examples, but recognize there's a big difference between little w, kilojoules per kilogram, and W dot, kilojoules per second or kilowatts. Okay, let's plan ahead. We need to look up S1 and H1 from the tables first. Then we're going to use the pressure table to look up our entropy values and enthalpy values at states saturated liquid and saturated vapor. And we're going to need all those to find X2I and then solve for work isentropic. All right, so let's go through the numerics of this. M dot, 12,000 kilograms per hour. We're going to transform that into 3.33 kilograms per second simply by using there's 3,600 seconds in an hour. Okay, then we're going to go to our steam tables, superheated for the throttle condition, 4 megapascals, 400 degrees C, and we're going to write down H, 3213.6, and S, 6.769 kilojoules per kilogram degree K. Always include your units when you're writing your numbers down. Then we'll go to the pressure table because we know the exit pressure. And we're going to write down these numbers associated with HF and HG, kilojoules per kilogram. Okay. HF, a low number. HG, a big number. Okay. SF and SG, entropy, kilojoules per kilogram degree K. Saturated liquid, a little number. Saturated vapor, a larger number. Well, that can remember, entropy is a measure of disorder. The higher the number, the higher the disorder. All right, so now we're going to move ahead. Okay, so let's see. I've written down my numbers I wrote out of the steam tables, and then I'm going to say that S2I equals S1. That's 6.769. We just wrote that down. So we're going to solve for X2I using the definition of quality. Okay, it's S2 isentropic minus SF divided by the quantity SG minus SF, and get 0.864, 86.4% quality. And then we're going to back solve. We're going to use the definition of quality X2I to solve numerically for H2I, because we're going to need that to determine the isentropic work. All right, so let's see. We should know this off the top of our heads. H2I is equal to the quality times Hg plus what's left over, 1 minus the quality, HF. Okay, got it. And so H2I is 2322.3 kilojoules per kilogram. I should have written my units out there. Shame on me. All right. We're looking for work isentropic. W isentropic, we'll use the first law, steady state, steady flow, one inlet, one outlet. Recognize that Q equals 0. Let's see, Q in minus work out equals H2 minus H1. So do you see that I didn't write out all my steps? W isentropic is H1 minus H2. I flipped the minus sign on the first law. Q minus W equals H2 minus H1. All right, so we're going to crank through it on the calculator to determine that the isentropic work is 891 kilojoules per kilogram. Got it. Next, what's the turbine efficiency? My claim is you should be able to figure this out without going to your formula sheet and without even going to your textbook. Turbine efficiency, it's a ratio. It's always going to be a number less than or equal to 100%. So you can figure out, let's see, what kind of turbine would give me the maximum possible power? Maximum possible power would be the reversible in adiabatic situation, a reversible turbine. But we know that we've got an actual turbine with irreversibilities. And so we should be able to figure this out. Turbine efficiency is W actual over W isentropic without a formula sheet. But don't punish yourself. If you're allowed a formula sheet, go for it. So W actual is the turbine efficiency times the isentropic work, kilojoules per kilogram. Okay. So we're going to do here's 891 was W isentropic, turbine efficiency. So our actual work, kilojoules per kilogram, 713 kilojoules per kilogram, a lower number. So finally, we're there. So we're looking for the power. We're not looking for for little work. We're looking for the power. That's simply going to be m dot times little w. Go through our calculator work. We've already converted m dot into kilograms per second. So we've got 2,377 kilowatts, or we'll write it out in a sentence. The steam turbine produces 2.38 megawatts of power. Boom. Looks easy once it's all laid out in front of you. The first time you're through it, go through it. It'll be a little tougher, but you got to get through it. Otherwise, you won't be prepared for your test. All right. Example 2, an air turbine. And so looking ahead, we're going to say, we've got air, it's an ideal gas. And in our instructions, we're going to say, we're going to treat this with variable specific heat, ideal gas with variable specific heat. Okay, here is a picture of what a commercially available air turbine looks like, and it is used for starting gas turbine engines when they're not running yet. How do you get an engine started? How do you get a gas turbine engine started? You use an air turbine. You take in compressed air from a land-based compressed air supply. The air flows into here. It runs across one single turbine blade stage. Just one stage is enough to generate enough power to start turning the gas turbine engine. And then at a lower pressure, the exhaust air just exhausts out into the surroundings. So that's what a commercially available air turbine looks like. Here's now, again, if you're trying to think about preparing for a test, this is a right down the middle of the fairway test problem. A fully insulated air turbine operates with conditions of 500 kPa and 27 degrees C and a mass flow of, I got to move my 1.5 kilograms per second. Treat the air as an ideal gas with variable specific heat. The turbine outlet pressure is 150 kPa, high pressure at the inlet, lower pressure at the outlet, but above atmospheric pressure. Changes in kinetic energy, negligible. Isentropic turbine efficiency, 85%. Okay. Two things, determine the output power from the turbine and the exit temperature from the turbine. Okay. Classic test problem. All right, so translation for treat air as an ideal gas with very specific heat. Air, it's an ideal gas with variable specific heat. That's translation. Use table A22 for the properties. Let's start with a sketch. Okay, you see, same idea, so I won't belabor this point. Your turbine sketch is supposed to look like the real world equipment. I've labeled our M dot going in will exactly equal M dot out since it's steady state, steady flow, open system with one inlet and one outlet. I've labeled the inlet conditions. I've labeled the turbine efficiency. I'm showing output power, and I'm showing the output pressure. That's all we know. What do we want to find? We want to find W dot of the turbine, and we want to find T2 actual. We'll start with a sketch. Now, where's the vapor dome? We've got an ideal gas. The vapor dome is down here, way down here where I'm wiggling my cursor because we've got an ideal gas. Okay, so we do need to depict this on a TS diagram without a vapor dome. We have an ideal gas. So we're going to show two lines of constant pressure, two isobars, one at 500 kPa and one at 150 kPa. The 500 kPa isobar is steeper than the lower pressure. These are curved lines, okay, but not very curved, okay. We're going to show the isentropic process. That's what we're going to analyze first, the solid line, reversible adiabatic. We're going to show the dashed line, that is the actual process. We going to the right, since it's adiabatic, S2 is going to be bigger than S1. S2 actual will be bigger than S1 because of the second law. Okay, and that's a decent sketch. That's a professional quality looking sketch for this problem. Okay, our approach is going to be nearly exactly like the steam turbine analysis, but we've got different property evaluations. We're going to be determining little W actual and then multiply that by the mass flow rate to get the power. We're going to study the isentropic turbine, and we're going to use a special isentropic ideal gas relationship to find T2 isentropic. More on that in a second. Once we find T2 isentropic, we can look up H2 isentropic. Okay. We will determine the isentropic work, W sub I. Once we've got H2I, we can look up H1. Okay. Then we will apply turbine efficiency to find W actual. W actual had better be a lower number than Wi, okay? And then we'll apply the mass flow rate to get the power. Okay, so planning ahead. Inlet conditions, we're going to look up H1. We're also going to look up a property called PR1. More on that in a second. In order to find PR2, okay? Once we have found PR2, we're going to use PR2 to back calculate T2 isentropic and H2 isentropic. And then we got it made. All right. So let's go to the air properties first. So relax. I'm going to tell you more about this. Maybe I better tell you about it now. We're at 300 degrees K at the inlet. So we will write down H1 is 300.19, and we'll write down PR1 is 1.386. Okay. Notice this column of PR. PR only applies, this property PR only applies when delta S is 0. These columns only apply for isentropic processes. That's important to remember. Okay. And PR is called the relative pressure. It has nothing to do, PR has nothing to do with the P reduced pressure associated with the Z, the compressibility factor. They're two totally different variables. And a lot of students get confused by that, but for the air tables, PR has nothing to do with the compressibility factor whatsoever. Okay, so now I want to talk about that. For an isentropic process, okay, for an isentropic process only with an ideal gas, with variable specific heat, P2 over P1 exactly equals PR2 over PR1. That's an important identity, and it's defined in your book better than I have explained it here. But please recognize it's only for isentropic processes. So we're going to be able to solve for PR2 since we know P2 and P1, and we just wrote down PR1. So PR2 equals that. So let's just do the math, okay? So we wrote down PR1. So PR2 is 0.4158. It's the number 0.4158, and it is unitless. It is unitless. And you can go to your book and see the background on that. So we're going to use PR2 to go back into table A22 to find T2 isentropic and H2 isentropic. Here we go. Use PR2 to back solve for those two. Okay, so now we're back to table A22. Our PR2 is 0.4158. Uh-oh. We're going to have to interpolate, aren't we? So we're in between those two PR values. So we're in between these temperature and enthalpy values. So we'll set up an interpolation table and quickly determine that T2 isentropic is 212 degree K and H2 isentropic is 212.4 kilojoules per kilogram. So, okay, so just to repeat, this using PR, PR2 over PR1 equals P2 over P1 only for isentropic processes, delta S equals 0. Okay, so we're going to move ahead. Isentropic, so we just determined H2I is 212.4. H1 we already looked up. So the isentropic work using the first law, this is not just a formula. This is first law for an adiabatic process, Q is 0, okay? And that's it. First law, steady state, steady flow, one inlet, one outlet. W isentropic is H1 minus H2I, 87.79. Turbine efficiency, figure it out. Don't use your formula sheet. The actual work is the turbine efficiency times the isentropic work, okay? And as I was preparing to give this little talk, I noticed here that I didn't turn H into Greek letter eta. So the work actual is, there it is, I made that correction, eta turbine times W isentropic. So I caught that error. Finally, we're looking for the output power. W dot is m dot times little w. We do the math, 1.5 kilograms per second times 74.62 to get 112 kilowatts. We're halfway there, okay? But we've got to find the actual outlet temperature. Okay. So let's see, the actual outlet temperature, H2A, we've got to go back and solve for H2A. We'll use the first law. So the work actual equals, so let's see, Q, that's 0, minus the work actual is equal to H2 minus H1, H2 actual minus H1. So we'll solve for H2 actual from the first law to get 225.57. Oops, we're going to have to interpolate again. So we'll interpolate, okay? And we're finding that T2 actual is 225.6, or in other words, we subtract 273 to get the air turbine outlet temperature is negative 47.4 degrees C. That is cold. That's some cold air. It's expanding. It's decreasing its pressure, okay, increasing specific volume. It's getting colder. This is the real thing. The turbine outlet temperature is negative 47.4 degrees C. All right, example 3. We're going to do the same problem, except we're going to use a different model for the ideal gas. We're going to say we have constant specific heat. I want to illustrate to you how you can solve this problem either way. So if you were in my class, this would be your test problem, because in most of my career, for ideal gases, I used ideal gas with constant specific heat in the vast majority of my engineering practice problems. This would be, if you're in my class, this is your test problem. Same words, fully insulated turbine, inlet conditions, 500 kPa, 27 degrees C, mass flow 1.5 kilograms per second. Treat air as an ideal gas with constant specific heat. Do not use table A22. Outlet pressure 150 kPa, isentropic turbine efficiency, exactly the same, and find the same things, the output power and the exit temperature. Now, so looking ahead, what's the translation for our model? Well, with constant specific heat ideal gas, H2 minus H1 equals Cp times T2 minus T1, because Cp is constant. Integral Cp dt. Okay, got it. Also, so we know that by heart. We don't need this. We don't need to get this off a formula sheet. We know this by heart if we've done enough problems. You may need to go to your formula sheet for an isentropic process with an ideal gas with constant specific heat. Isentropic process, ideal gas, constant specific heat. PV to the K is constant, where K is Cp divided by Cv, and for air, K is 1.4. I've got that memorized because I use that so much in my engineering practice. K is 1.4 for air. So now we're going to solve the problem, right? Sketch. The sketch is identical. Identical sketch. Identical TS diagram. See, there's no properties there. Well, there are properties. Pressure, temperature are there, excuse me. No enthalpies, no entropies tabulated there. Exact same TS diagram. All we're going to do is change the way we determine our enthalpy and deal with entropy. Here's our approach. Our last step, well, we're looking for W actual. We'll multiply that by M dot to get W dot actual, the power. Okay. We're going to study the isentropic turbine, and we're going to apply this isentropic relationship for ideal gas constant specific heat. P1 V1 to the K equals P2 V2 to the K, and we're going to derive what T2 isentropic is. So we're going to get one equation and one unknown for T2 isentropic equals a formula. And we're going to derive it. We're not going to look at the formula sheet. Then we will determine the isentropic work using the first law. Okay. just like we did from before, except we're going to get H2 minus H1 differently, easier. Okay. We're not going to have to do any interpolation on this approach. We'll apply turbine efficiency to find W actual, and then finally get the output power. Oh, and then we're also going to have to go back and determine T2 actual from the first law. Okay, so let's plan ahead. We need K if we don't know it in our heads. We need CP for air, probably don't have that in our heads, and we'll use the inlet condition to get those. So there we go, table A20. We're going to use the inlet condition 300 because it's easy. CP is 1.005 and K is 1.4. We write those numbers down. We're going to analyze the isentropic turbine first. And we're going to say for an isentropic ideal gas, constant specific heat, P1V1 of the K is P2V2 of the K. What I'm looking for is T2 isentropic. I don't see it in my relationship. But I remember the ideal gas equation of state. V is RT over P. I solve for V. I put that in my equation. Okay. I use algebra. To simplify my equation and solve for T2I. So I'm not going to drag you through this. If you don't see how to do this quickly, download the static slides associated with this video and study how to do this. Now, this may be on your formula sheet if you're allowed to have one. What are the restrictions on this formula? I hate saying that word. What's the formula? Ideal gas, constant specific heat, isentropic process, reversible and adiabatic. So all those things apply to this formula. Okay, very restrictive. Okay, but it applies to what we're doing, isentropic analysis. Okay, so we go through with our input numbers, and we find that T2 isentropic is 212.68 degrees K, absolute temperature. Boom. Next step, determine W isentropic using the first law. Much easier than table work. It's H1 minus H2I. That's the first law, Q equals 0. Well, for an ideal gas with constant specific heat, H1 minus H2I is CP times T1 minus T2I. We just found all these things, okay? And so the isentropic, well, we just found isentropic work. We did not do that yet. Here it is. Pardon me, I wasn't looking at my work. T2I, here it is, okay? Work isentropic is CP times T1 minus T2I. So we get a number for W isentropic, 87.76 kilojoules per kilogram. Now we're going to use turbine efficiency to look for W actual. I should be able to figure this out. Shouldn't need a formula sheet. W actual for the turbine is going to be less than the isentropic. So I'm going to multiply by the turbine efficiency, 74.59 work actual, multiply by m dot that we have given. So we've got 111.9 kilowatts. And so in a sentence, I'm going to say the air turbine produces 112 kilowatts of power. That would go on your test solution. The air turbine produces 112 kilowatts. We still need to determine the actual outlet temperature. Find T2A. We're going to write down the first law for the actual process, 1 to 2A. W actual is equal to H1 minus H2A, Q is 0. So ideal gas, constant specific heat. Enthalpy change is CP times delta T. Back solve for T2A. It is 225.78 degrees K, so we'll subtract 273 and get negative 47.2 degrees C as the air turbine outlet temperature. That's going to go on my test solution. All right, now time to recap the air turbine analysis. So we are near the end, okay? Let's tabulate what we got numerically for each ideal gas model. There's our problem statement. We did the identical problem first with variable specific heat, and we got 112 kilowatts output power and negative 47.4 degrees C outlet temperature. Then we said, let's use constant specific heat. We got 112 kilowatts of output power. We got negative 47.2 degrees C. How would you as an engineer compare those two results? They look mighty darn close to each other, don't they? So look, so don't split hair. Which approach is correct? For this situation, both are correct. Both are correct. And so don't let anybody kid you that functionally as a practicing engineer for this situation, both approaches work perfectly fine. If you're trying to figure out how much power you're going to get from this turbine to start up a gas turbine engine, man, you're golden with either approach. And similarly, outlet temperature. Don't you see that if you're measuring temperature with a thermocouple, you're going to pretty much get the same result either way. Okay, so let's recap these three example problems. Adiabatic turbine analysis is similar for both phase change substances, steam, and air, any ideal gas substance. The difference is in the evaluation of the thermodynamic properties. Okay. What's your approach for each of those? Study the isentropic process. I didn't say start with a sketch. That's step 0. Study the isentropic process. Apply turbine efficiency. Determine the actual process results once you've applied turbine efficiency. I would say it's as simple as that. It's not simple. It's tough, especially when you're doing this for the first time. When you've done it hundreds of times or 1,000 times, it gets pretty easy. But you've got to practice to get better at this. I hope this has helped. I hope it's given you some ideas on what some typical test problems might be. So good luck in your practicing of these analysis. And I'm going to move on to videos, I hope, for compressors, pumps, and nozzles similar to this.